Hi everyone, this is the chi-square lab with the M&Ms or Skittles, depending on which class you were in. And one of the things that we start with is our null hypothesis. And with our null hypothesis, we were stating that there was an equal distribution of candies, specifically each color of the candy itself. Now, when you look at the cup of the candies itself, the number of M&Ms or Skittles should have been 30. So because there were 30 M&Ms or Skittles, when we look at the distribution of colors, if I could spell right, we were expecting even numbers of each of them. So I'm going to fill out my color classes here. So red, orange, yellow, green, blue. And since there are 6 colors and there were 30 M&Ms, the expected value for this lab is 5. Again, we have 6 different classes. Each color is equally distributed, so there should have been 5 colors of each. When you get your cup of M&Ms, there may not be exactly 5, but what we want to find out is if there are not exactly 5 of each color, is it still within an acceptable range of how many there should be? And just looking at the data, or just looking at your M&Ms, you may think to yourself, yes, something is wrong. We do not have an equal distribution of color because there's only 1 yellow. Or we don't have exactly 5 blue. But you can't just state that without having your chi-square analysis to back it up. So what you do is you take the number of actual M&Ms or Skittles that you were given, and again, we expected 5 of each color, and what we do is we count up how many there were in the actual cup. So for red, we are observing 6. Get these out of the way. For orange, we were expecting 5, but we observed 4. There was only 4 in our cup. For yellow, we expected 5, but there was only 1. For green, we expected 5, but there were 6. For blue, we expected 5, but there were 7. And then for the brown, we expected 5, but there are 6. And so these are the observed values for the M&Ms in our cups. Now, this table is very handy in that it breaks down each step for you. You may not get this table on an FRQ, or you may get a table that's similar but slightly different. Just keep in mind that you need to be able to do each of these. And if you look at the formula sheet is not a table set up like this. But it does tell you that you're still doing the sum of your data. So what we're going to do is we're going to do the observed minus the expected. So the 6 minus 5 is 1. 4 minus 5 is -1. 1 minus 5 is -4. 6 minus 5 is 1. 7 minus 5 is 2. And 6 minus 5 is 1. Don't worry about these negatives, because in this part right here, we're going to square the value. And when you square it, it gets rid of the negative. So 1 squared is 1. -1 squared is still going to be 1. -4 squared is 16. 1 squared is 1. 2 squared is 4. And 1 squared is 1. So notice, again, no negative values here. Now we're going to take the observed minus the expected squared, so that's this value, and divide it by our expected value. And it's important that you guys do not round any of your decimals until your very final answer. Once you start rounding here, 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 once you start rounding too soon, you introduce rounding error. And you don't want to do that, because then your number will come out really close. But you've got to be careful, because it could push you outside of the tolerance range that College Board sets down. So for those of you guys who are not familiar with these calculators, it does give you the ability to square. There is a button there, and it does give you the ability to square root. Although we're not doing that here, it does give you the ability to square root. Please get used to these calculators. These are the calculators you're going to use on every test, every FRQ, and the AP exam. So even if you have your own calculator, you're not going to be using it on our exams or on our calculator or on our FRQs. So 1 over 5 comes out to 0.2. And so I can go ahead and fill that all in for all the ones that are 0.5. Now I'm going to do 16 divided by the expected value of 5. That comes out to 3.2. And now I'm going to do 4 divided by 5. 4 is our observed minus expected value divided by that expected value, and that comes out to 0.8. And then for your chi-square, what you're going to do is you're going to add all of these numbers up. And this comes out to 4.8. So that is the sum, and the sum is the chi-square. Do not take the square root. Do not square this number. That is the chi-square. For your degrees of freedom will always be the number of options minus 1. So in this case, since we had 6 options, 6 minus 1 is 5 as our degrees of freedom. You can look up the critical value in your notebook, or you're also going to have a separate formula sheet. We always use that p-value at 0.05. And then what you're going to do is you're going to look across this row to where your degrees of freedom are. So starting here, we're going to go across until we hit degrees of freedom is 5, and that's the value we're going to compare our number to our chi-square. So our chi-square is 4.8, that critical value is 11.7, and since the chi-square is lower than that critical value, we fail to reject the null hypothesis. And this is very important. It's very important that you include in your reason the because. If you don't put this, you're not going to earn any points. So we failed to reject the null hypothesis because our chi-square value of 4.8 is lower than 11.7. And that's it. That's how you would state your conclusion. That's how you would justify whether or not you reject or fail to reject the null hypothesis.